Hello, and welcome to the AI Research Roundup. I am Alex, your host, and today is May 11th, 2025. Alright, so today we are looking at a research paper from Hugging Face's trending list, published just 4 days ago, titled PrimitiveAnything, Human-Crafted 3D Primitive Assembly Generation with Auto-Regressive Transformer. This paper introduces a new way for AI to understand 3D shapes by breaking them into simpler geometric building blocks, an approach called primitive abstraction. It uses an auto-regressive transformer, which is an AI model that learns to assemble these primitives sequentially, much like humans do, by studying many human-created examples. Okay, so this first figure really gives us a great visual of what the authors are achieving. We see a whole collection of colorful 3D objects, things like animals, furniture, and even the word SIGGRAPH spelled out. These are all constructed by the PrimitiveAnything system, using those simpler geometric building blocks or primitives like cuboids and cylinders. It demonstrates how the system learns to assemble these primitives into complex forms, showcasing its versatility across many different shape categories, a key goal of this research. Building on those impressive examples, this next figure details the PrimitiveAnything system's architecture. It shows an input 3D shape first becoming a point cloud, which is a set of 3D data points representing its surface. Then, an ambiguity-free parameterization, a method ensuring each primitive is described consistently, defines its properties. The core auto-regressive transformer, guided by the shape in existing primitives, sequentially adds new ones using a cascaded primitive decoder, a component predicting each primitive's attributes, like class and position, one after another. This really shows their step-by-step assembly logic. Alright, so for that auto-regressive transformer and its cascaded primitive decoder to learn effectively, the way primitives are described needs to be unambiguous. This figure illustrates a problem called primitive attribute ambiguity. It shows how a single cuboid, due to its symmetry, could be defined by different rotation and scale parameters yet appear identical or very similar. This potential for multiple descriptions for the same thing can confuse the learning model. The ambiguity-free parameterization we discussed earlier tackles exactly this, ensuring each primitive has one consistent definition, which is crucial for stable training. Okay, so with that ambiguity-free parameterization helping to stabilize learning, this table then dives into some hard numbers. It compares the 3D segmentation accuracy of PrimitiveAnything with other learning-based methods, specifically on a chair subset from their human prim test data. We see metrics like the RAND index, or RI, which gauges how well the AI's component grouping matches human ones, with higher scores being better. Then there is variation of information, or VOI, where lower values mean closer agreement, and also segmentation covering, or SC, another measure where higher is better. PrimitiveAnything, shown as ours, consistently shows superior performance. So those quantitative results really underscore the benefits of the PrimitiveAnything approach. In essence, this work shows how reformulating 3D shape understanding as a sequential human-like assembly task using that auto-regressive transformer leads to more intuitive and accurate results. Learning from human examples and handling primitive ambiguity allows it to create decompositions that are geometrically sound. For example, by using a chamfer distance loss, which measures differences between point sets and achieving high voxel IOU, a metric for 3D volume overlap. Crucially, these decompositions also align better with human perception. That is all for this AI Research Roundup. Thanks for tuning in, and I am Alex.